we are discussing handling of deadlocks. We have seen some preventive methods. Today, first, we shall see an avoidance method. The basic principle of the avoidance method has been given here, okay, that all processes have to declare the maximum need of all resources types at the very beginning. When a process asks for a resource, the algorithm dynamically checks whether the allocation should be safe or not. What do I mean by safe? I'll explain. If safe, then the allocation should be done, else the process waits. Okay. Now, let us give an example to show the basic principle of this method. Okay. Suppose that we have a banker, right, and the banker has rupees 1,000 crore available with it, okay, which the banker gives loan to the different projects, right? Let there be projects like this, say P1, P2, P3, okay, PI. So the key number of projects are there. Maximum funds needed by this project, let me say R1 hat, R2 hat, R3 hat, RI hat, and say RK hat. Okay, that is the maximum amount needed. And let currently the amount that has been allocated, okay, say the allocated amount, current allocated amount be R1, R2, R3, note that the projects will need the entire amount at the same time. The projects will need this amount in installments, and the banker will release amounts in installments, okay, and that is this current allocation. And say now the reserve fund that is with the banker, that is left to the banker, say this is the banker, and say this is RR, okay. Now that's the situation now, and say right at this moment the process PI asks for, or the project PI asks for an additional amount of RE. Now when it asks for an additional amount of RE, if the banker loans that amount, okay, in that case the money that will be left to the banker is RR minus RE, say this is equal to RL. Now banker now will see that whether allocations of this money to the project PI is safe or not. What does it do is this, it tries to find out a sequence of the projects, basically a permutation of the projects, such that the first project of this permutation, when allocated the entire amount, the rest of that entire amount, if that is available with the banker, whether that project can finish or not. If that project finishes, in that case the entire amount that was taken on loan can be returned to the banker, and that banker in that case can allocate the amount to the second project. Second project can then finish and then return all the money that it has taken on loan to the banker, and that way if all the projects in that sequence can be completed, in that case that allocations of the fund to the process PI, that additional amount is safe, otherwise it is unsafe. Okay. Now to clarify, say the banker says, checks that whether there exists a sequence that means a permutation basically of the projects, say P1 dashed, P2 dashed, P3 dashed, say Pi dashed to say Pk dashed, okay, with the current allocation possibly say R1 dashed, R2 dashed, R3 dashed, Ri dashed to Rk dashed, okay, whether RL is sufficient to meet the rest of the requirement of P1 dashed or not. If it's so, then that amount will be given on loan to P1 dashed, then P1 dashed can finish. That entire amount it has taken on loan can be returned to the banker. The banker then checks whether the rest of the amount of P2 dashed that P2 dashed will need can be given on loan or not. And if it can be given on loan, okay, if it can satisfy the rest of the amount, then P2 dash can finish, and then it can return that entire amount to the banker, and so on. If starting from P1 dash to Pk dash, okay, all the projects can finish, then the amount that will be given on loan, that RE amount given on loan to the process Pi is safe, otherwise it is unsafe, okay. Therefore, the matter lies that a safe situation, a safe state is that there will be a sequence that all the projects can finish, okay. This is what is the banker's algorithms is. Let us, in our case of an operating system, let us see what can be the situation. Say a particular systems have say 10 tape drives, okay. So there are processes P1, P2, P3. The maximum need of the tape drives, that processes P1, P2, P3 are all running. The maximum need of process P1 of tape drives is 9, that of P2 is 3, and that of P3 is 7, okay. Current allocations is 4, 1, 1, and therefore reserve is 4, right. Right at this moment, you see that the situation is like that, okay. Now, if P2 asks one more tape drive, whether that tape drive can be allocated to P2 or not, it is a safe state, and the safe, because a safe sequence exists, okay, P2, P1, P3. For example, say another P2 asks another tape drive, okay, therefore allocated will be 1 plus 1, which is 2, reserve will be 3, okay. Now you see, since there are 3 reserve and maximum need of P2 is 3, therefore 1 can be allocated to it, and 1 that allocated is there, in that case P2 can complete. If P2 completes, okay, then it can return everything that was taken from that reserve. That means all the tape drives it has taken can return it to it. In that case, the number of tape drives will be 5, right? Its need is over. Out of these 5 tape drives, 4 can be allocated to P1 and P1, sorry, 5. All the 5s can be allocated to P1 because P1 maximum need is 9, allocated is 4. Therefore, 5 can be allocated to P1. Then P1 can finish. It will return all of them, and the reserve will be now 9. And with 9, 6 more can be allocated to P3. P3 can finish, and all the tape drives can be returned back to the banker. Therefore, you see there exists a safe sequence, and therefore the tape drive that has been requested by P2 can be allocated. Okay, this was a situation, and therefore we can say that this is a safe state. Okay, if P2 asks one tape drive, but just check in a similar way that say original value was 4, that if P3 asks 1, let us see what is the situation. Okay, so P3 asks 1, therefore it will be 1 plus 1, which is 2, this will be 3. Now you see with these 3, P2's maximum need is 3, okay, that 2 can be allocated to it, 2 more can be allocated to it, P2 can finish, then P2 will return all the tape drives back, therefore number of tape drives the reserve will have is 4, right. Now see, if the reserve is 4, P1 needs 5, maximum need is 9, allocated is 4, therefore P1 needs 5, the P1 cannot complete, P3 also needs 5, 7 minus 2, that is 5, therefore P3 also cannot complete because only 4 tape drives are available, right. Therefore, such a situation we call an unsafe situation, and if it's an unsafe situation, in that case the banker, that means the operating system, the management operating device management systems will not allow the tape drives to be allocated to P3 and P3 should wait, okay, till we can come to a safe situation for P3 to be allocated one more tape drive, right. Now, this is a situation when the banker has only one kind of currency, but the situation is that the banker will have different kind of currencies like say dollar, pound sterling, francs, rubles, and so on, okay, and therefore, and the projects will need different kind of currencies, right. Like in an operating systems, there will be different kind of resources, and the processes will need different kind of these resources, right. Now, let's see in such cases what is to be done, okay, what should be our algorithm, okay. Now, just before we formally give the algorithm, let me just show you for your noting that what I mean by a safe state. By a safe state will always lead to a non-deadlock situation, and if it's an unsafe state, then there is a possibility of a deadlock, okay. An unsafe state does not mean that there will be a deadlock. I think that you should realize that unsafe state doesn't mean that it will be a deadlock, but there is a possibility of a deadlock, okay. Now, for avoidance, what we will do is this, that ensure that the system never enters an unsafe state, and that is the crux of the algorithm of, okay, that deadlock avoidance, right. Now, we present an algorithm which is quite famous algorithm, we should say. We call that banker's algorithm. This is we call a banker's algorithm because of the similarity with the banker's problem that I have just talked of, okay. Now, let's first give the data structures. The data structures are that there will be a vector available M, okay, that means a single dimensional array, the maximum dimension is M, which gives a number of currently available resources of each type, okay. For example, that if available ith entry of the array available is P, that means that P number of resource type I are available, okay. Now, similarly, there will be another array, two-dimensional array, say max nm, right, that is the maximum requirement of each process, okay. For example, if max ij is q, it means that process pi, the process pi can request q number of resource type rj. That can request means the maximum number of resource type rj the process pi can request is q, okay. That is kept in a two-dimensional array, say max nm. Then another array we will use, which is that allocation nm, okay. That allocation nm is also a two-dimensional array. This gives a current allocation. For example, if allocation ij is r, that means that process pi has been allocated r amount of resource type rj, okay. process Pi has been allocated R amount of resource type Rj. And there is another matrix that will keep, that is that need nm, a two-dimensional array once more. Need ij is max ij minus allocation ij. That means for any entry here that gives that what will be the needed, a subsequent need of a process Pi of a resource type Rj. Okay, that is the need, max ij minus allocation ij. Okay. Therefore, these are the four data structures or the four arrays we will be using: available m, max nm, okay, allocation nm, and need nm. Naturally, we are assuming that the number of processes is n and the number of resource type is m. Okay. Now, let us define now one comparison of two vectors. Say x and y are two vectors, so both of length n. Then we will be defining x less than equal to y if and only if for all I xi is less than equal to yi. Okay. I am assuming that x and y are both of them vectors. Both of them have length n. That means both are represented by one-dimensional array of dimension n. Then x less than equal to y means that for all I, xi will be less than equal to yi. For example, if x is, say, a 5-dimensional vector, x is 5, 3, 2, 6, n. The different components of x, the 5 components of x are 5, 3, 2, 6, n, and of y are 10, 3, 4, 9, 9. In that case, since for every element, okay, xi is less than yi or equal to yi. For example, here it is equal. Oh, sorry, here it is equal. Here it is equal. We call x less than y. Okay, sorry, x less than equal to y. Okay, and we say that x less than y if x less than y and x less than equal to y, we say that x less than y if x is less than equal to y and x not equal to y, then x is less than y. Okay. Now we are almost ready to give the Banker's algorithm. We first will define a function we call safety. Okay, this safety function will detect whether it is a safe state or not. Okay, therefore safety is a function which detects whether the present state is safe or not. All right. Now this uses two more local arrays. Okay, one is the reserve m, which gives the current reserve of resource types. That means if reserve m is equal to reserve I is equal to p, then our I type resource has p elements left in the reserve. Okay, and there's another array that will be one-dimensional array that will be using another vector which is of Boolean type, right? Finish n. This gives the process status, right? Therefore, two more local variables. One is reserve m we will be using, another is finish n that we will be using. Okay. Now, first step of the safety function is that we initialize first all available. That available is made equal to reserve. That means available is assigned to reserve. And for all I 1 to n, finish I is made false. Okay, therefore for all the processes, okay, the finish I is false. That means all the processes finish state is false. Okay. Now this, let us see the other steps. The step 2 is that find an I such that both these are true. That means find finish I is equal to false and need I is less than reserve I. That means we take a process which has not finished and its current need is less than equal to reserve, that it can be met by whatever is in the reserve. Okay. Naturally, if no such I exists, we come to step 4. We'll see what we do in the step 4. Otherwise, that reserve is incremented by allocation I, which means that the process I can finish, its needs can be met from the reserve. Therefore, after finishing process I, it will return all its allocations to the reserve. Therefore, the reserve ultimately will be incremented by allocation I, and we can in that case declare finish I to be true, which means that process I can go to completion. Okay, and this will go back to step 2. We continue over here till we come to step 4. Now here if we find that for all I, finish I is same as true, that means all finish I is true, in that case the system is safe, right? Otherwise system is unsafe. Therefore, since if the system is safe, we will return a true value. If the system is unsafe, we will return a false value. Therefore, basically this safety function will check whether if an allocation has been made, whether that allocation is safe or not. That means whether there exists a sequence of processes which will, okay, one after the other will finish in such a way that all the processes can ultimately go to the finished state. Okay. Now, this algorithm, which is a resource allocation algorithm, will take help of this safety algorithm, and let us see what is the resource allocation algorithm is, right? Here we declare another array, okay, which is a request vector of pi. Okay, that means right at this moment, what is the request of each process pi is kept by this vector. Now, in the case of step 1, if we find that request I is less than need I, okay, that means whatever has been requested by the process is less than or equal to its current need, right? I mean, it's further need, then naturally we proceed, otherwise it's an error situation. Okay. Now, step 2 is that if request I is less than equal to available I, okay, that means whatever at present is available, if the request I is less than equal to that, only then we proceed, otherwise the process I goes to a wait state. Okay. Now, if we proceed, then first we allocate the resource virtually, not actually, but virtually we allocate the resource, okay, and then update the different vectors. Okay. Available is reduced by the request I, allocation I is reduced, is incremented by allocation I plus request I, and need I is decremented, reduced by the request I. Therefore, these are the updation that is done on these vectors available, allocation I, and need I. Okay. After that, we call the safety routine. Now, if the safety routine returns false, naturally the process pi has to wait, because in that case the allocations will be unsafe, right? Otherwise, allocations is safe, and therefore we can actually allocate the resource, right? Therefore, this is what in a sense is the banker's algorithm. Okay, and let us try to see through an example that how the banker's algorithms works. Okay. Now, say this is a situation. I have taken here that there are 3 resource types, R1, R2, and R3. The amount that is available with the system is R1 equal to 5, R2 7, and R3 9. Okay. There are 5 processes, P0, P1, P2, P3, and P4. Maximum requirements of the different resources have been shown, R1, R2, and R3. Okay. So, for example, for process P0, the maximum requirement is 0, 2, and 9, right, which it has declared earlier. Similarly, for P1 it is 536, which it has to declare earlier, okay, and so on. Here in these columns we have shown the current allocation, okay. Here the current allocations for P0 is 0, 2, 3, for P1 is 1, 0, 0, and so on, right. And you can see that available therefore right at this moment is 3, 2, 2. For example, R1 has been allocated, 2 have been allocated, then 3 are left because R1 total availability was 5. Similarly, R2, 5 have been allocated, 2 will be left, and here 7 have been allocated and 2 is left, right. Now, even in this situation, okay, you see if this be the situation, in that case this is a safe situation because there is a safe sequence P3, P4, P2, P0, P1. That means say permutations of P0 to P4, P3, P4, P2, P0, P1 gives a sequence which is a safe sequence, which means that if P3's requirement, further requirement is satisfied, what is the P3's further requirement? It will be 2 here, okay, since max is 2, 2 here, 2 here and 1 here. Now, if that can be satisfied, which means these resources can be allocated to P3, then P3 can go to completion. After completing, it will return all its allocated resource to the reserve, okay. Then with that allocations of the reserve, okay, it can allocate the requirement, the full requirement of P4, P4 can finish and so on, right. Therefore, this is a safe sequence and therefore, this is a safe state. What I suggest is this, that you note down the status as has been shown, right, and you really work out by allocating and deallocating that this is a safe sequence, okay. Now, let us come to this, right. The P3's request right at this moment is 0 to 1, right. You can once more check with this state, if P3's request is 0 to 1, there exists once more a safe sequence, say P3, P4, P2, P1 and P0, and therefore, this request can be granted. It's still in a safe situation, right. But if we take P1's request, right, instead of this one, right, instead of in fact this one, if I take the P1's request which is 311, okay, it is an unsafe. That means you will not be able to find any sequence of the processes P0 to P4, a permutations of P0 to P4, such that all the processes can go to completion, okay, with the resources that will be available at successive instances of time, okay. Therefore, this is an unsafe situation and therefore, what it will be done is that P1s would be kept to an wait state, right. This in fact or in essence is deadlock avoidance, right. You can see unlike deadlock prevention, which creates a situation that resources will not be allocated until and unless that the process can go to completion. That means the resources will not be allocated, will be allocated only when that any of the 4 necessary conditions are not satisfied, at least one of the necessary conditions are not satisfied, okay. In this case, in the case of an avoidance, what is done is that resources are allocated, okay, maximum requests are known. As the process continues, the requests are allocated, okay, and every time it is allocated, before allocations it is seen whether that this situation is safe or not. If the situation is safe, then only the allocation is made, otherwise the allocation is not made, right. Therefore, it is somewhat better than prevention, okay, that we'll have to allocate the resources at the very beginning, right, whether it is needed or not. Here, the resources are allocated when it is needed, only if it is safe, though it may, even here it may so happen that resource is allocated much earlier than actually it is being used. Therefore, here also the problem of low utilizations of the resources remain, right. Now, that's all so far as our resource, I should say that the deadlock avoidance algorithm is concerned, this algorithm, as I've already said, is called the Banker's algorithm, and it's quite a well-known algorithm. Now, the other thing is that, other possibility is that we allow, we'll be more daring. That means we'll allow the deadlock to happen if it happens at all. Okay, and once it happens, we'll detect that there is a deadlock and we'll try to recover the situations out of the deadlock. Okay, now this is called deadlock detection and deadlock recovery. Let us see that what we mean by deadlock detection and deadlock recovery, right? Now, if it's a single instance of each resource type, right, then what we do is this: we convert the resource allocation graph, which I have shown in the very beginning, okay, into a wait for graph, and then check for the presence of a cycle. Okay, let's see. Let's give an example. This is a resource allocation graph. Here are 5 processes: P1, P2, P3, P4, P5, and here are 1, 2, 3, 4, 5 resources also. As I told earlier, the resource allocation graph, so this resource is allocated to P1 and therefore is held by P1, right? Therefore, all these pink arrows, okay, are allocation arrows, right? Assignment arrows. But this is allocated to P1. This resource is allocated to P2. This is allocated to P3. This is to P5, and this is to P4. Okay, and there's only single instance of each resource, and therefore no dot inside has been shown, right? And the request stages have been shown here by black. So this is a request stage from process to a resource. This is another request stage, and so on. Now, to detect in such a situation whether there is a deadlock or not, what is done is this resource allocation graph is converted into what we call an wait for graph. This is in fact the wait for graph, right? Here, this resource nodes have been withdrawn, and so for example, a assignment node and a request node followed by an assignment node will be collapsed into a single edge, right? For example, say P1 to P2, these two edges have been collapsed into a single edge here, right? Similarly, these two edges has been collapsed, so P2 to P3 has been collapsed into a single edge here, right? The resource allocation graph, in that case, this way has been converted to a wait for graph, and we can apply the available techniques of detecting whether there is a cycle or not. And if there is a cycle, for example, here it is a cycle, it means that a deadlock situation exists. Okay, then P1, P2, P3, P1 is a cycle. Similarly, P1, P4, P3, P1 is a cycle. This means that P2 is waiting for a resource to be released by P1, okay, right, or rather it is reverse. P1 is waiting, okay, for a resource to be released by P2, okay. Similarly, P2 is waiting for a resource to be released by P3, and so on, right? And since a cycle exists, it's a deadlock situation. Therefore, in the case of the situation that if every resource type has only a single instance, then this particular algorithm can be used. And naturally, the cycle detection algorithm has a complexity of the order of n square, and therefore this algorithm will have a complexity of the order of n square. Now, the problem arises that instead of a single instance of every resource type, if there are more instances of the resource type, in that case, we have to go for an algorithm, right, which is more or less similar to that Banker's algorithm. Let us see that what is done here, that the data structure that we'll be using here is that available M is a vector, m component vector, right? This gives us that number of currently available resources of each type, similar to the Banker's algorithm that we had taken an available m. Similarly, there will be an allocation nm, which gives the current allocations of the resources of each type to each process, right? For example, the allocation ij is q. In that case, pi processes, okay, q number of resources of the type rj has been allocated to the process pi. For example, if allocation ij is equal to q, it means that q amount of resource type rj has been allocated to the process pi, as was done in the Banker's algorithm also. And here's a request nm, that means the current request of each process of each resource type, right? For example, if the request ij is k, it means that process pi is requesting q more instances of the resource type rj. Whatever has been allocated over that, k amount of more instances of the resource type rj is being requested at this instant of time, right? Now, let's see what is the DeadLock detection algorithm. Here also use another vector, right? An array of dimension m, right? Which says that what is the current reserve of the resource types, okay? And a finish n, which is of type Boolean. Okay, let us see that what is the initialization. Step 1 is initialization. We initialize that available to reserve, as was done in the case of Banker's algorithm also. You can make a comparison with the Banker's algorithm. Now, if allocation I is non-zero, that means every component of allocation I, okay, right? If every component of allocations I equal to 0, then naturally we'll put finish to be true. But if at least one component of allocation I is non-zero, right, then finish I will be assigned to false. Okay, false will be assigned to finish I. Right, therefore, that finish I equal to false means that the process pi, at least one resource type, okay, has an allocation non-zero, right? In that case only, that false is assigned to finish I. Now let us see the other steps of this algorithm. The other steps is that from the processes we find an I, okay, such that both finish I equal to false and request I is less than reserve I. This checks that whether the current request can be met at all or not, okay. Whereas in the case of a Banker's algorithm, we were checking, right, that the current need is less than reserve or not, okay. Therefore, here is the difference with the Banker's algorithm, that here we check that whether the current request I is less than reserve or not, and in the case of Banker's algorithm, we check that whether the current need is less than or equal to reserve or not, okay, and check whether finish I equal to false. If no such I exists, we go to step 4. Let's see what we done in step 4. Otherwise, that allocation is done, okay, right? And if that allocation is done, right, then reserve, we assume that on with this allocation, whatever has been allocated to that the process pi will return it and the reserve will increase, okay. Which means here also we take an optimistic view that we assume that whatever has been put forward as a request right at this moment, if that request is met, then the process can go to completion. Naturally an optimistic move, okay. And on that, we expect that the allocated amount will be returned and therefore reserve will increase. We assign true to finish and go to step 2. Okay, we continue the loop over here. And when we come to step 4, step 4, we check whether for some I, finish I is equal to false. Now, if finish I is equal to false, then the system is in a deadlock state. And the process Pi is essentially deadlocked, right? This is what is our deadlock detection algorithm, consisting of these 4 steps, 1, 2, 3, and 4, and these data structures. Okay. Now, complexity of this algorithm is of the order of n squared. Now, let us take an example, okay, to see. Say, currently, this is a situation. That we have the resource types initially with the system R1, 3 instances of R1 and so on, R2, R3, R2 is 7 and R3 is 7. Now, 5 processes, current allocation is this, current request is this, and available current is this. Okay. For example, now R1 will be 1 because 2 have been allocated, originally it was 3. Now we can see that with this, what I say that note this down, this assignment, this state, and see that no deadlock situation exists, and there is a safe sequence, so to say, P1, P3, P0, P4, and P2. Okay. Therefore, this is not a deadlock situation, right? Now, if now P3 requests 0 to 0, okay, which means P3's request is, what is that P3? P3 request 0 to 0 here, then you can check, okay, that immediately the system goes to a deadlock, okay. Therefore, you note down this, that and satisfy yourself that this is not a deadlock situation as stands here, right? But if P3's next request turns out to be 0 to 0, right? In that case, it immediately turns out to be a deadlock situation. Now, one important thing that I should mention here about this algorithm is this, that I say that it is a rather optimistic algorithm in the sense that it believes that whatever is the current request, if that request is made, the process can, with that, if that request is made, the process can go to completion, right? Now, naturally, that may not happen, and if it may not happen, in that case, what will happen that there will be a deadlock later on, and in that case, while that particular process will request a resource, okay, or any other process will request a resource, okay, the deadlock will be detected later on. Therefore, deadlock being not detected right now, but deadlock will be detected when another process possibly will request for some allocations of the resource, right? Now, that is quite fine that deadlock has taken place and our algorithm detects some deadlock, okay, but what is the recovery, okay? Now, the recovery from deadlock is naturally that you'll have to abort processes, okay. One is that start aborting processes. What can be done is that all deadlock processes is aborted at one time, or one process at a time is aborted until deadlock is broken. In any case, naturally the entire thing is very costly because many actions have been taken which will go to waste. The problem may be that process may be updating files, and in the middle of that updating files, okay, abortion makes issues complicated. And another is that some irrevocable actions might have been taken, like for example, some checks in the banking systems may have been printed and all have to be destroyed, okay. But if you have to recover from deadlock, some actions have to be taken, okay, and therefore some wastage will be there. Another possibility is that start preempting resources from processes. Okay, as you start preempting resources, it may happen that the processes will come out of the deadlock. Okay, that's another possibility. Therefore, now situation may be that how frequently that deadlock detection algorithm should be run. Okay, one can run the deadlock detection algorithm, okay, intermittently. For example, maybe that it is automatically scheduled, or one can run the deadlock detection algorithm when a particular process makes a further request of resources. Okay, now one can choose any of these options, okay, and go for running the deadlock detection algorithm. Now, coming back to termination of the processes, right? Which process, if it has to terminate in steps, should terminate? Okay, the different factors naturally should be considered are that priority of that process, which is being planned to be terminated, how much computation has already been done, and how much is yet to be done, right? Because that will determine the cost of abortion, right? And third is how many and what type of processes have been used, what type of resources have been used. If it's a costly resource that has been used, naturally that process should not be terminated, okay, if it's possible, right? There may be other factors also like this, which should determine that if we are going to terminate processes in steps, which processes should be terminated. But in any case, cost is twofold, and cost may be quite high. Firstly, the cost is the running cost of detection algorithm. Okay, it has its own cost because it has to be run intermittently, and recovering cost whenever you are aborting it. Okay, and basically when you are trying to recover from the deadlock, you will have to pay a penalty in terms of wastage of resources, right? Now, that's all that I would like to discuss so far as detection algorithms are concerned. And in the very beginning, we talked about that deadlock handling, that there are essentially three methods. One is the prevention, one is avoidance, and is allow deadlock, detect it, and recover. We talked about another, okay, here, say third method, and the third method is essentially that don't do anything, okay. Pray to God that deadlock will not happen, but let the systems starts moving, starts running. Possibly deadlock will happen sometime or other. Okay, in that case, the processes will get stuck, the resources will get stuck. Okay, the throughput will fall, and in that case, that operator interventions may be needed. Check whether there is any the throughput degradation is there or not, and then operator intervenes and possibly starts from the very beginning or starts aborting processes to recover the situation. That's all so far as deadlock handling is concerned.